So welcome everybody to this session. I hope it is now started. Can you see my screen? I hope you can. Fine. Okay, there it is. Good. Welcome to the session on historical surveying, the Dutch roots to the profession. Let me show you what you can expect. First of all, welcome to all, and those of you presenting, you will recognize the pictures and you will be able to present the content of these pictures. We have two moderators in this session. That's me, Lisa Groenendijk, and Tim Brouwer. And we have the following 7 presentations, or at least being sent in to this FIG working week. And I put them in a timeline starting from the most old one. That's the one related even to the 16th century before Christ by William Jörg from Switzerland. Unfortunately, he will not be able to present, so you will not see him today in this session, but it's worthwhile to have a look at his paper. Then in 1339, the rule will talk about the medieval porcelain charge, and is particularly the mystery part of this typical charge. Then we have in 1766, Camilla and Teresa will tell us about the Danish slave cadastre on St. Croix. Then already more recent, 1806 till 1845 approximately. Then it is the time for Chris William Wynne to talk about the Dutch Boers, the Boers of Dutch descent in South Africa. 1873, 1838, Kelly Henderson. We expect from her a presentation on joining the dots from the Adelaide Plains in Australia. I hope she can join us because till now she has not yet been able to join us in the session. We will have from 1929, 1937 approximately. That's the period that Huub Ekkelenkamp will be covering, the Dutch mapping of Indonesia. And the youngest, maybe the youngest presenter, now I don't know if he's the youngest, but at least he is the most recent one, 1887, 1966, Bart Root from the Netherlands about Professor Wening Meines. We have a program with some presentations of about 12 minutes and 3 minutes of questions. We have some video presentations of about 4 to 6 minutes, and we have a quiz. The first one to start is Huub Ekkelenkamp, and he will present the Dutch mapping of Indonesia. So I would like to give the floor to Tim to introduce Huub.
Yes, thank you, Lisa. I will be introducing the speakers today throughout the session, as well as ask the questions that you as audience will be placing in the Q&A within Hopin. So if you have any questions, place them in the Q&A. Our first speaker, and therefore I want to share my screen, is Huub Ekkelenborg. Ekkelenkamp. I have some trouble sharing my presentation at the moment, but Huub is studied electrical engineering and telecommunications in Delft, in the Netherlands. He also promoted in the Department of Geodesy in 2019 on the role of Dutch presence in Indonesia in the development of geodesy in the Netherlands. And he's also active in Stichting de Hollandse Cirkel, which is translated in English, the foundation for the Dutch Circle, which is mainly focused on the preservation on geodetic heritage in the Netherlands. And Huip will be giving a presentation on the Dutch mapping of Indonesia. Huip, are you with us?
Yep.
The floor is yours.
Thank you. Can you see my first slide?
Yes, we can see your first slides.
Oh, sorry. All right. Welcome, everybody. I will try to give you an overview of the Dutch mapping of Indonesia, which took place more or less between 1800 and 1990. And I will do my best to give you also a little bit of background, how this mapping originated. Give you a little bit information about the Netherlands and Indonesia. Indonesia is quite a distance from here. We have about 1,500 kilometers sea travel. This is quite a long distance. Sailing time is about 100 days via the Cape of Good Hope. It's a long way, and therefore it was very much appreciated when the Suez Canal was dug in 1869. It was much shorter, and it resulted in a travel time of about 50 days. But you can imagine that in the beginning it was difficult to get an answer on your question, sometimes more than a year. Indonesia is quite large. It's 2,000 times 5,300 kilometers, and it's much larger than the Netherlands. It's 51 times bigger, and only the island of Java is 3.5 times the Netherlands. It gives you a short historic overview. It started with the United East Indies Company already in 1600. They had 200 years focused on trade, and when Napoleon conquered large parts of Europe, Holland became occupied by the French, and so there was a French-English period in Indonesia, in the Far East, and after that the Indonesian part, the Indies, became part of the Kingdom of the Netherlands. But the Netherlands required that they could pay for their own costs. So they introduced a cultural system, which means it was obliged to grow certain products, and that was a difficult period for the Indonesian people. But after that, there was an enormous blooming period. A lot of engineers got opportunities to develop the country, to develop infrastructure. But that all ended with the Japanese occupation, and the 3.5 years resulted in a total change of the colonial situation. After that, everybody expected a new phase. There was an independence struggle, and after the independence, which came in 1949, there was a period of unrest, but after that the focus was on infrastructure development, and the population grew tremendously. Yeah. This is an overview of the archipelago. It gives you an idea of the enormous different country than we have in Europe. You have the main island, which is Java in the center. You have Sumatra on the left, Kalimantan on the north, and you see that there are many, many islands, about 18,000 islands. And you see also a little bit about the comparison with the size of the Netherlands in the little map on the right-hand side in comparison to the enormous area of Indonesia. The first thing was, of course, the approach of Java. Java was in the center, the most important island. And you see here one of the first maps from 1854. And it's remarkable that this surveyor, Melville van Carnby, he was a hydrographer, so he focused on the sea travel, and he drew profiles of the volcanoes, which you can see at the bottom of the map for orientation. On the right map, it's the approach to Batavia. The ships entered from the south, and so they had to turn in this bay, and one of the first islands they met was the Isle of Onrust, where all the ships were repaired, and you see that there on the map. It's from 1853. The first surveys were volcano surveys, and especially a guy called Jung Hoon, he did a lot of work. He climbed all the volcanoes and mapped them, and he made one of the first detailed maps of the hundreds of volcanoes, especially on Java and some of them on Sumatra. And you see his sketch at the bottom, and he colored them, and so they were quite famous and standard in those times. A little bit about Java. In 1920, it had 30 million inhabitants with only 500,000 Europeans. But nowadays, it's over 130 million inhabitants, which is half of the Indonesian population. You can read all the details also in my handout, in my paper. It gives you some different maps, so together with this presentation, it should give you a good overview. Already in 1856, telegraphy and telephony started via aerial lines, and a lot of survey work had to be done to install these cables and microwave transmitters, long wave transmitters. And a lot of telecommunication went along railways, because then you could announce a train is coming, be aware. And so therefore the telecom network has a close relation with the railway network. And the railway was about 5,000 kilometers. It was bigger than in the Netherlands. Here you see a nice map of Batavia, as it was called in those days. Now it's Jakarta, of course. And you see a lot of railways in the city. And this is a map from 1945. So it's at the end of the occupation, you could say. You see the airport here, airfield. And you see from the harbor, Tanjung Priok, railways along these lines all the way to the big plantations for transport of goods and people. An impression of some government buildings is given here. The town hall, it's now a museum. You see the church, now called Emmanuel Church, 1839, and an important post and telegraph office, which is still in operation today. All three buildings are still existing and are still used, and especially have interest for tourists. But Jakarta has changed, of course. It's a city with many faces. The top photograph is looking north. You see a lot of high-rise buildings, and in the south you see close by the volcano Salak. So in almost every place on Java you see volcanoes, and they are a potential threat to the people. So surveying volcanoes is quite important. Here you see an old map of 1923 already made, very detailed, 1 to 50,000, and the railways is going from Jakarta, Bandung, to Bandung. Those days it was called the trip from Batavia via Buitenzorg, Bogor nowadays, all through mountainous area, and here you see a tunnel and a cable car, and so it's a quite difficult surveying work, and a lot of local people were involved, but the whole organization, I will come to that later, of the topographic survey never had more than 600 to 700 people on the payroll, and they did this immense country in a very short period. The radio communication to the Netherlands was so important because I told you that messages took sometimes 100 days one way and 100 days the other way. So radio was one of the most important infrastructures there. And here you see an antenna, which was at that time in 1923 the largest and strongest transmitter in the world. So it's a long wave transmitter, and the aerial, the antenna, is hung between two dead volcanoes, as you can see. Details you find in my paper. Navigation and location fixing, if you do such a long trip and you have so many islands, it's important that you have a profile of the mountains, of the volcanoes, for which you use some sophisticated instruments. So surveying, navigation, location fixing was right from the beginning very important. And you see some of the important sextant, station pointer, and a chronometer at the bottom. Then everything was based on surveying, yes, and for that surveying, triangulation, topographic maps, and sea charts were, of course, important. You see a map here from Sumatra, and you see the triangulation in the red lines, and here, just above this Toba Lake, there is a base laid out for measuring, and from there on, of course, all the triangulation started. Some instruments used here in this survey work are shown in this slide. These were important for accurate measurements over long distances.
Sorry, I have to interrupt. You have 1 minute left.
All right, I go faster, but I'm almost finished. Here you see the universal instrument. You see all kinds of theodolites, and most of you will be aware of that. The results in 1939 show that most of the western part was mapped, was surveyed. You see that in the small triangles. On the eastern part, it was not yet finished, and that was done by later photogrammetry. The international world maps were produced in 1926, and this is a nice example of the details of this western part of Java. My last slide, almost, is an overview of some details. North of Bandung, you see here is an observatory. They had an own observatory to watch the skies, and from there on time signals were sent all over the peninsula for longitude measurements. Conclusions. The geodetic education training in the Netherlands owe much to the obtained knowledge. There were many things which benefited the Netherlands. Of course, for all building projects, maps were made, but we should not forget the unbelievable commitment by local people as well as foreign, often European surveyors. Without their help, it was never possible. And it gave us in Europe a better understanding of all the environmental influences. But the past cannot say to us what we have to do, but can say what we should not do. And that's my last ending. Thank you very much for your attention.
Thank you very much, Huip. Unfortunately, we don't hear the applause from the audience at the moment. That's kind of different than during the live sessions. But interesting presentation. I haven't seen any questions for you, but I want to encourage the audience as well to think of questions for Huip's presentation. Put them in the Q&A, and after this session there will also be an Ask Me Anything session where we can go into discussion about Huip's presentation. For now, I think we will switch over to the next element of the program, and that is a video. A video by Camilla Knudsen and Teresa Tode from Denmark, the University of Aalborg to be exact. There they are, very good. They have made a video on the Danish slave cadaster on St. Croix in the US Virgin Islands. And we would like to show you that now. So I will be sharing that tab from my screen. And playing it.
Hello, my name is Therese and this is Camilla, and we are from Denmark, and we have written a project about the Danish cadaster on St. Croix. Our project started with a wonder. The wonder was, how has the property registration functioned at St. Croix compared to Denmark, and what significance does the land register at St. Croix had in the society of that time? Early in the process, we discovered that the purpose of the cadaster was to collect taxes, but the property perception was not the same. So what was the difference? We started to look in the old cadaster in the archives, and we could see in Denmark they registered the property and what crops there was on the properties. On St. Croix they did the same, but they also registered slaves. And what we could see here in the picture of a cadaster was that they registered a slave, and they registered a capable, what was adult slaves that could work. They registered 6 slaves, they registered half adult slaves, and they registered children slaves. And for each adult slave that could work, they have to pay 1 staler, and for each half adult slave that could work, they paid a half staler. So they could see how much they have to pay for the slaves in the cadaster. That means that a slave was attached to the property, and therefore you could own a person. In the project, we also explored what did the early Danish surveyors do on St. Croix. Through old instructions for the surveyors, we discovered that they made a survey method that preceded the United States survey method. Here we see one of the first maps of St. Croix. The survey method they used on St. Croix was based on guidelines. Here we see the first guideline who was surveyed. The next guideline was the center line, and the third guideline they surveyed we see on the map. Through these guidelines, they surveyed quarters, for example, the Queen's Quarter or the Prince Quarter. And in these quarters, they surveyed properties who were squared properties. Today, we see many prints from the Danish surveyors. For example, the center line, who is now the main road on the island, and many of the names in the quarters is still the same today. If we compared the 2 surveying methods, the one on St. Croix versus the one in US, we can see that both surveying methods create these guidelines. In St. Croix, it's called the center line, and in the US, it calls geographic lines. And both methods create this square properties out of the guidelines. So the surveying methods was nearly identical. They just call the guideline different names, but the meaning of the methods was the same. The meaning for the surveying method was to create a method that was easy to survey on undiscovered landscape. All Rwanda created a new wonder that was the Danish surveyors the first to use this survey method, or do you know anyone else who was prior with the method? Because we discovered that the United States was not the first.
Yes, thank you. Yes, great video by you, Teresa and Camilla. Thanks for your contribution here. I don't think I see any questions for you for this video, but I want to again encourage the audience, if they have any questions for you, to put it in the Q&A, and then in the session afterwards we can answer those questions and go into discussion with each other. So again, thank you very much for your video and to take the time to come here.
Yeah, thank you. Thank you.
Then we move on to our next speaker, and that will be Bart Rood.
Hi, good afternoon.
There's Bart. Hey, Bart.
Hi.
Yeah, Bart will also be joining us with a live presentation. Bart is an assistant professor at Delft University in Technology, and he will be giving a presentation on a very interesting topic on the Around the World with Professor Fenik Menes on the first gravity measurements in the ocean.
That's correct. Thanks, Tim, for the introduction. Hello, my name is Bart Rood, and I'll take you along a voyage by Professor Fenik Menes around the world, starting in Den Helder, and we'll discuss a little bit on his work, and especially because he was the first to make accurate gravity measurements in the oceans, and I'll explain you why he does it in the oceans instead of on the oceans. This was a project I did during my PhD, and I was asked by the TU Delft to look at the work of Fenik Menes, and why it all started with a suitcase. And this was the suitcase. So the Heritage Depot of the TU Delft received this suitcase, and it was full of diagrams, notebooks, papers, measurement rolls. And this suitcase contained a lot of information. And the TU Delft Library asked a group of us, and I was asked to be the scientific advisory, as my research is on gravity data. And could we translate all this information, not only the books, but also some instruments we still had in the depot, and bring it out to the public, and maybe even talk a little bit about the work done at TU Delft and other universities. So who is Professor Fenik Menes? He was born on 30th July 1878 in Scheveningen, which is close to Den Haag. And he was a professor in his lifetime at the TU Delft and Utrecht University. His research area was geodesy at the TU Delft and geophysics at Utrecht University. But his expertise was really on gravity data, so measuring gravity and trying to interpret what we see. And he was, of course, a globetrotter, traveled the world and doing measurements all over and talking about geosciences. We see him here at the basement of the KNMI building, where he did all his calibrations of the instrument, and we see a part of it in front of him. So we named the project after his publications, Gravity Expeditions at Sea. And the goal of the project was basically, can we conserve this Dutch cultural and technical scientific heritage? And how can we do this best way possible and bring it to the public? And also for my university especially, can we do at the same time a lot of outreach on geodetic and geophysical work, knowledge, and not only the books and the information, but also some objects. How can we give them to back to the public, because they were gathering dust in the depot. I already give the end result, but it's a nice image as well in how we presented this. We used one of his voyages, one of his most famous, the voyage on the K-18, the submarine K-18, where he did his measurements. And we built an interactive website where you can follow him and read about the life on board the K-18, but also the measurements and findings he did during this voyage. The voyage went from Den Helder up way through 3 oceans, the North, the South, and the Indian Ocean, and following all the way to Surabaya. And at this website, Wikipedia, expeditiewikipedia.nl, you can follow him. And the voyage started in Den Helder, as I said, on the 14th of November 1934. And everybody in the Netherlands waved them goodbye. Well, everybody who had a bicycle back then. And you can, if you squint your eyes, you can really see Vening Magnus aboard the submarine. He's always quite visible in these images because he's 2 meters tall, so always a head taller than the rest. And it was really an event. The band was playing. A lot of newspapers were there. The collaboration with the Navy and a scientist was applauded. Introducing the main players, we have Commander Hetterschei, the commander of the submarine, and his lieutenant, Lieutenant Wiedema, who also carried a camera. So there is a black and white movie about this voyage. Very, very slow, but nice to watch, and tells the tale of the K-18 voyage. And here we see Vening Magnus and the other officers. And I use this voyage to explain the public what is gravity, what can we do with it. And I always start with this image. This is the data the Vening Magnus took for the during the 8 months, and these are the 240 gravity measurements he took. And I plotted it chronologically, and we see it's 9.81 meters per second, which we learn in Holland as the value G. But you see along his voyage, it changes. And I don't see any structure in that, but that changes when I plot these data sets, not chronologically, but with respect to where they were measured on a latitude. So where with respect to the equator. And look what happens. So we see the equator now in the middle. We have the South Pole to the left and the North Pole to the right. And we see a nice parabola showing the shape of the Earth. The Earth is not flat, we all know, but it's also not spherical. It's a little bit squished like a rugby ball, making the gravity data less in the equator regions and more in the polar regions because you're closer to the center of mass. Of course, we already know this, and the nice thing of this project, people are now know that I work on gravity and pendulums, and the people in the library at the TU Delft found a very old dissertation where a Dutch mathematician worked already on the project pendulum experiments to determine the shape of the Earth. It was, however, in Latin, and I had some Latin in my high school, but not that good. So we asked Marius Goossens to translate it. And we found very nice collection of all the pendulum data back then in 1830. And it showed similar shapes. But what was nice of Vening Magnus' work 100 years later was that he opened up the oceans, because all these measurements needed a stable platform. And on a rocking ship, this is difficult to obtain. And he built a machine that was capable of measuring the gravity with high precision, even on board a submarine. And that is this instrument. It's called Het Gouden Kalf, the golden calf, maybe because of its color, of course. And we see here, I like this picture because we opened up the machine and really showed the bowels of this machine. And this is the main heart, which normally is inside this canister. And we see 3 pendulums are basically the measurement principle. So we use the pendulum equation to measure the motion. And he captures these motions by little mirrors on the pendulum, and he hits lights on it, and these lights are reflected back in a dark chamber on photographic paper. Why 3 pendulums? Because with the pendulum equation, of course, you only need 1 pendulum. But we have the rocking ship, so we need to decouple the motion of the ship from the motion of the pendulum in affected by the gravity. So he used a pair, and by looking at the difference of this motion, he could extract the motion of the ship. But why 3? Well, and that's nicely shown if we look on top of the machine. I have a top photograph here, and I marked the light rays with colors, and we see the red and the green. He measured really 2 pairs, and a proper geodesist always measures twice. Why? Because you can take the average, so you have an average value, but also the difference between already gives you an uncertainty of the estimate of your observation. And that's where you can see a proper geodesist between a professional one and an amateur one. And a professional geodesist always measures twice. I tell this my students because they always do things once, and I say, but how well do you know your value? Then always measure twice. And also some extra corrections, because he already knew if I want to go to high precision, I need to correct for many things, tilt, atmosphere corrections, and other things. So he built this machine really for precision, and therefore he could map a gravity field. And I like this one, especially with Huib's presentation. This is the map of Indonesia, back then the East Indies, where he mapped the gravity field of that region, but in the oceans. And he found these particular zones. Back then they were called the Veening-Meines belts. And I want to get that name back, because now we call them subduction zones. But Veening-Meines belts were aligned with the volcanic regions of the islands of Indonesia, and also the seismicity that was there. And geophysicists were still thinking of what is this, and this extra data hinted at something of going down. Veening-Meines didn't believe that the crust could break, so he was against plate tectonics. But his measurements do show that the crust goes down here. It's a negative anomaly. So he had the information, but not yet the will to accept plate tectonics. And the nice thing is we also compare this data now with the data I used from satellites. And we see basically, I try to make the color scale in the same region. We see, okay, we have a little bit higher resolution, but the same features, the same geophysical features can be seen in his data already 100 years ago. And I think this is incredible. And this shows his engineering and creative mind, and really focus on the accuracy. And this is what geodesy is about. Know what you're measuring, but also how accurate can we get this measurement. And this is what one of the outreach messages is. This is really what Veening-Meines wanted to show. So at the end of the project, we were able to put this story and the equipment, and we had help of students from Amsterdam, the history students, to put it in museums. So you can now go to the Maritime Museum in Den Helder, and there is a permanent installation about this voyage with some interactive designs. I had a teaching lab at the TU Delft where I could show this to all the teachers. We have a teachers environment where we can show this story. But the instruments are now put there in the Science Center. It's only a few more weeks because the Science Center is moving. But if you're in Delft, please go there and you can really see the instrument at its best. I hope to, after the move, to bring it back into the public, because I think this instrument really shows geodetic and engineering ingenuity. So to conclude, Professor Vening-Meijners opened the oceans for gravimetric research. His observations would help study geophysical processes like plate tectonics and isostasy of volcanic islands. So really giving new tools, new insights of processes on Earth. And the ingenuity of the apparatus at that day made it the only device capable of doing accurate gravity measurements in the oceans, because he was in a submarine 30 meters underwater, until the 1950s, when different apparatuses were. So for 30 years, it was the only device measuring gravity up to 1 or 2 milligal. So all the people that worked on there, and we are now busy because in our search we found other literature. We found letters to Mr. Harry Hess, friendly letters, because he was discussing his wife and giving success. And Harry Hess is one of the founders of plate tectonics, and we want to really make a connection between Vening-Meijners and the ideas of plate tectonics, ironically ignored by Vening-Meijners. So thank you for letting me speak here, and have a nice session.
Yes, thank you, Bart. Interesting talk. Amazing how good the accuracy is they could get those days. There's one question for you. Did Vening-Meijners ever admit he? Yes, thanks. Did he ever admit he was wrong about what we now call plate tectonics?
Yes, yeah. That's always the question that's asked. But so plate tectonics was accepted in 1967 by the scientific community after the magnetic data. He died in 1966, so he was always able to not admit that plate tectonics was the way to go. So no, he did not admit that plate tectonics was a theory.
Good. Okay. Thank you for the answers. If there are any further questions are asked, maybe we can bring them to the Ask Me Anything session.
There is one question from Clifford Rogers.
Yes, but let's take it to the. Let's keep that question and take it to the Ask Me Anything session. I think for now, I want to thank you, Bart, for your presentation, and to move on to the next speaker. And the next speaker is actually in the form of a video, Chris Williams. I think he is here as well. Chris Williams-Wayne, welcome.
Thank you, Tim, and welcome to all the audience, if I can call them that. I will ask you to start the video presentation in a short moment, but I do just want to say that it's very good to have had Hate's presentation before mine, because it showed the position of the Cape in relation to the Netherlands in the north and the East Indies in the east. And the main reason why the Cape originally was developed was because this was a station that was created to provide supplies to the ships that traveled between the Netherlands and the East Indies. I also want to just say that there is a lot of history in South Africa, and I have touched on many of the histories of the indigenous groups in the past, but because this was an e-working week that was organized in the Netherlands, I have concentrated in this instance only on the people of Dutch origins in the Cape. So over to you, Tim, and the email.
Yes, thank you very much. So, like I said, Chris Williams-Wayne has sent in a video on the Boers of Dutch descent under British rule in South Africa. I will start the video now. Apologies, I just noticed there is no sound on this. I will try again.
Greetings from South Africa. In 1652, the Verenigde Oost-Indische Company, VOC, which is the Dutch United East India Company, established a victualling station at the Cape. In 1657, the VOC agreed to grant land parcels to free burghers, former employees of the company who decided to stay on in the Cape to increase the production of fresh food. Based on Roman Dutch law, the VOC introduced a system of diagram and title deed, initially a single document to record ownership. The settlement expanded eastwards and northwards. The further they migrated from the original VOC settlement, the less committed the burghers became to supplying the company with produce. As they continually moved away from the Cape in search of better farmland and freedom from obligations to the VOC, they became more dependent on livestock. These burghers became known as the trekboers, describing their lifestyle of living and moving in wagons pulled by a span of oxen. There were sporadic conflicts between the trekboers and the indigenous Khoikhoi herders and the San hunters. The conflict involved the three needs of the trekboer: land, cattle, and women. Exclusive use of a land parcel was a foreign concept to the indigenous people, whose wealth was in livestock. Peace could generally be maintained through judicious distance or assimilation between the frontiersmen and the indigenous groups, which was not uncommon. By the end of the 18th century, the trekboers had extended their migratory occupation as far as the Great Fish River, although very few titles had been issued except for Irvine in the administrative towns of Swellendam and Graaff-Reinet. In 1806, the British occupied the Cape in response to Napoleon claiming the Netherlands. The extent of the colony was defined in 1809, as can be seen by the pink shade on the map on the screen. The extent of the colony was deemed to be Crown land unless it had been verified by a diagram and deed as held by a free burgher. Most trekboers did not have a surveyed diagram or a registered title deed confirming their allocation. Land occupied by the indigenous peoples was deemed to be Crown land. By 1814, the Cape Colony had formally ceded to Britain by a convention under which Dutch vessels were entitled to resort freely to the Cape of Good Hope. Britain thereby agreed to pay £5 million sterling to the United Netherlands for the Dutch possession. And then in the 1820s, about 4,000 British settlers were settled on the volatile eastern frontier as a buffer between the Cape Colony and the indigenous tribespeople. Many of the trekboers were dissatisfied with the British government of the Cape because 80% of them by 1837 had not yet received title to their farms. Many trekboers left the Cape in search of a new land. They became known as the Voortrekkers. The Voortrekkers established de Republiek der Hollandse Zuid-Afrikaanse Immigranten in het Land van Natal. 3 towns were laid out: Pietermaritzburg, or Pietermaritzburg, as the capital, Congela, near the Bay of Natal, now part of Durban, and Wenen. Initial land records were lines in a ledger, the simplest form of a cadaster. By 1841, the Volksraad passed a law. Land tenure would be freehold. Every Voortrekker who had come to the Republic before the beginning of 1840 was entitled to 2 farms and 1 earth in any of the 3 towns. And then came the British again. In 1843, the British did not want Natal, but the Boers were deemed to be rebellious British subjects who had to be forced to acknowledge their allegiance to the British Crown. The British annexed the Boer Republic van Natal. Yet again, the British could not keep the Boers in Natal for the same reasons as in 1837. Although some Boers decided to stay, most chose to leave the Natal colony, and several Boer republics were created to the north. These Boer republics were left to self-govern until the discovery of diamonds and gold. And that's a story for another time.
Yes, thank you very much, Chris, for that video presentation. Interesting to see something coming from South Africa. I feel like we've really been moving to different parts of the world, different historical periods. And we're not finished yet with this program. We still have 2 presentations to go. The next presentation will be given by Roel Nicolai. Roel?
Yes, hello. Thank you, Tim.
Great. Welcome. Well, to introduce you, Roel studied geodesy in TU Delft and has a PhD from the University of Utrecht. I know you have been working for Shell for some time during your career, and you're also, but you have since retired, and you're also now the chairman of the foundation of the Dutch Circle, which I explained. And today you're going to give a presentation on medieval portolan charts, a geodetic historical mystery.
Indeed, this is my, like Bart and Huibs, is my PhD subject, and I look forward to tell you about this.
Great.
So, can I start?
Yes.
Tim, thank you for the introduction, and good afternoon, everyone. The origin of portolan charts has been hotly debated even in medieval history and the history of cartography for more than 1.5 centuries, and is still unclear. And my research adds a geodetic perspective to this. Portolan charts are hand-drawn charts on parchment. They are the first nautical charts ever and appeared like a bolt from the blue in the mid-13th century Mediterranean around Genoa or Pisa in the world of maritime trade without any involvement of the intellectual clerical elite. They show with an astonishing degree of realism for a medieval map the Mediterranean, the Black Sea and the Atlantic European coast as far as the Netherlands actually, reasonably accurately. They're in fact only accurate within this blue rectangle. Outside that, the coastlines become sketchy. This particular chart measures about 1 meter by 75 centimeters, which is fairly typical for a portolan chart. Their most astonishing feature is the good agreement with the Mercator projection, as you can see from the overlay in red. However, the Mercator projection was not developed until 3 centuries later. These charts are not perfect. The map image is rotated anti-clockwise by about 10 degrees, and there are significant regional scale differences. The Atlantic coasts are shown too small, but the Black Sea is too large. The total absence of any development path of these charts is very odd. They appear fully developed and in the blue rectangle do not develop any further. This accurate core area is basically copied for centuries. Finally, portolan charts are the first maps drawn to scale and equipped with scale bars that look like letters, 5 on this chart in the yellow ellipses. The Italian word for letter is scala, and this is where our word scale comes from. To analyze their accuracy, I selected pairs of identical points, one on the chart and the corresponding point in a modern dataset, 836 on this particular chart. I computed a least squares fit of the regions of the Portland chart to their modern equivalents on the Mercator projection, and that allowed me to identify several self-consistent subsets of points which are rotated and shifted relative to one another and have their own distinct scales. The mean point error of each regional chart is quantified as the root mean squared error of the least squares fit. The division into regional datasets is fairly consistent for all charts. The mean accuracy computed for 7 charts is about 11 kilometers. Rotations relative to geographic north of these regional point sets vary between 2 and 12 degrees anti-clockwise, and their scales differ between minus and plus 15% from the mean. In other words, there are substantial differences between these point subsets. And these angles and scales also vary between charts, but less than the range that I mentioned. The inference is that these point subsets correspond with regional charts, pieced together into a mosaic by medieval cartographers who did not know the exact scale and orientation of each regional chart, possibly by matching overlapping sections of coastline, as you can see here in this area. Rectification of the regional charts of the 1339 Portland chart yields this improved match with the Mercator projection. The red outline is the Mercator reference data set, and this image allows the extraordinary accuracy of these charts to be appreciated. That is extraordinary for a medieval chart. And that brings us to the aspect that is even stranger than their high accuracy, namely the excellent agreement of the coastlines with the Mercator projection. Map projections were unknown in the Middle Ages, and medievalists and map historians therefore consider this to be purely fortuitous or even automatic, a byproduct of the simple arbitrary charting method of the presumed medieval cartographers who would have ignored earth curvature and magnetic declination, which, that is the latter, was unknown until the end of the 15th century. However, this explanation flies in the face of common geodetic sense. It is generally assumed that medieval sailors dutifully recorded course and distance sailed during their trading journeys. However, the accuracy of the presumed medieval navigation techniques would fall short by a factor 10 or 20 compared to what would be required for Portland charts. But we cannot go into the details now. I approached the problem of the map projection by simulating the presumed medieval mapping process. I started by computing the correct bearings and distances on the ellipsoid between the points of a realistic medieval trading network, offsetting the bearings by the magnetic declination for the year 1250, which I obtained from a paleomagnetic model. I then plotted this in the medieval way. I did the same for the Eastern Mediterranean and Black Sea. Joining the dots and adding coastal details would create a so-called simulated Portland chart. The key questions are, how similar is such a simulated chart to a real Portland chart? Does it fit equally well to the Mercator projection? And to answer these questions, we need to abandon the pretty pictures and dive into statistical testing techniques normally used for quality control of geodetic networks, and by the way, by automatic face recognition software. The key quality measure for any geodetic network is the mean squared error, the sum of the squared weighted residuals divided by the number of redundant observations. When the measurements are Gaussian distributed, this MSE will be Fisher distributed, named after Ronald Fisher, who introduced this test in the 1920s. When the MSE of the network divided by its expected value, which is here indicated by sigma naught squared, is greater than a predefined tolerance, we will conclude that there is an error in one or more of the network measurements. This mechanism may thus reveal the presence of errors. Fisher's work was highly praised at the time, but in 1933, Jerzy Neyman and Egon Pearson showed that there is more to this problem than Fisher thought. When there are gross errors in the data, these errors will introduce a bias or gross error in the MSE. But the random errors are also still there, and therefore the biased MSE also has an error distribution, the so-called non-central Fisher distribution, which is shifted to the right. The real bias or gross error is shown by the block arrow at the top, and it is the difference between the expectations or the theoretical mean values of the two distributions. When the MSE value of a particular geodetic network is smaller than the tolerance, but in the red overlap zone, we have no reason to suspect that there are errors in the network when we apply Fisher's criterion. However, in reality, we can't be sure to which error distribution that value belongs, the one without gross errors on the left or the one with gross errors on the right. And when it does belong to the right-hand distribution, we have just made a so-called type 2 error, sometimes called a false positive, whereas the black zone introduced earlier by Fisher is called a type 1 error, also known as a false negative. Normally, the bias B is unknown, and the best we can do is compute the value of B that yields exactly an overlap zone of 10% or 20% of the area under the right-hand curve, which gives us an idea how sensitive the network is for undetected errors. This is also how automatic face recognition software works. Back to our simulated medieval networks. In this case, we know what the errors are. The distance errors due to ignored Earth curvature can be calculated exactly, and the ignored magnetic declination has already been estimated from a model. Analyzing the three networks of the Western, Eastern, Mediterranean and the Black Sea in the same way as the real Portolan chart again yields an MSE for each of the three networks, but because there were no random errors in the simulated dataset, this MSE is the actual bias that would be present in the MSE of a real Portolan chart had it been constructed using that simulated medieval method. The expected, or rather the mean accuracy of the actual Portolan chart, sigma naught squared, or this 11.3 kilometers squared, must be factored in. The real question is now, how large is this bias B for each of the three networks? Does it stand out sufficiently to be statistically significant, or does it hide inside the 11.3 accuracy band of the real Portolan chart? Knowing the magnitude of the bias B allows us to invert the Neyman and Pearson principle and compute the area of the red shaded overlap from the previous slide. That is the probability that the map projection is an artifact, a coincidental feature. The probabilities or p-values computed from these known biases, which I computed for each of the three networks, turn out to be extremely small, except for the Black Sea. And that means the probability of the Mercator projection being coincidental or an automatic artifact is extremely small. These numbers need to be multiplied with one another to get the probability that the map projection would be coincidental in the entire Mediterranean and Black Sea. The actual relationship of the two error distributions for the Western Mediterranean network are shown by the graph. And that demonstrates that the biased MSE values would have a clearly distinguishable, distinct value range here instead of what we would expect here. This geodetic quality control technique, normally used in control networks, is therefore instrumental in understanding the map projection property of these remarkable charts. The conclusions of this analysis are as follows. The map projection cannot be a coincidental feature or artifact, which means that it must be intentional. Portolan charts are mosaics, which were most likely made in medieval times by matching overlapping coastal sections of existing regional charts, which would have been maps or charts on a Mercator or similar projection. They cannot be medieval. The accurate geo-information on the coastlines can only have its origin in pre-medieval times. Portland charts are simply too sophisticated to be medieval creations. And this implies that geodesy is a lot older than is generally believed. I thank you for your attention.
Thank you, Roel, for your presentation. I know I'm learning a lot seeing all these presentations. It's really blowing my mind, the amount of how much perspective they had in these olden days. I haven't seen any questions for you, Roel, but I know there will be questions we can answer in the Ask Me Anything session. So that's also why I want to thank you for your presentation here. And also want. Sorry, what did you say, Roel?
My pleasure.
Yeah, great. And next, I want to introduce our next and final speaker of today, Kelly Henderson, all the way over from Australia. Welcome. Can you unmute, maybe?
Hello. Hi.
Hi. There we are. Good. Yeah. Thank you for joining us. You will be giving us a presentation on joining the dots analysis of trigonometric surface of the Adelaide Plains.
Yes, and thank you for helping with the technology.
Yes, we will see how far it goes. I see I will guide you through the PowerPoint because it's hosted on my machine, but I only see a black screen now. I'm not sure why that is.
Ah, there we go.
Can you see now?
Yes, thank you.
Good. Then I will stop sharing my screen and you can tell me when to click.
Okay, thank you. Good afternoon, good morning, and good evening. This presentation publishes research by John Porter and myself, if you can click please, which is the culmination of collaboration spanning 2 decades. John's research on South Australia's first surveyor, General William Light, is a small, albeit highly significant part of a far larger body of work extending to more than 1,000 of South Australia's cadastral surveyors, covering 150 years of the state's surveying history. If click please. And you can see that he's creating a biographical dictionary. As a preeminent expert on Light's survey, John was invited to present his research to the Royal Geographical Society of South Australia, published in 2007. And following 2 individual papers on Light and the Adelaide Survey at the FIG Sydney Congress in 2010, Jan de Graaf, the Honorary Director of the International Institute for the History of Surveying and Measurement, was invited to South Australia, and his visit to Adelaide initiated the Trigg Station Monumentation Project. This is a click please. This is an ongoing enabling project raising public awareness of the District of Adelaide Trigonometric Survey and its potential for World Heritage nomination as the world's first coordinated cadaster. Click again, thank you. At that stage, 2 of the Trigg stations were well known, and click the Flagstaff at Holdfast Bay on the coast, and again, click the master station, Trigg Station A, the commencement point for both the chain survey of the City of Adelaide and the District of Adelaide Trigonometrical Survey from the Mount Lofty Ranges foothills to the coast. And for those who like to read the fine print, down there in the very bottom right-hand corner on John Arrowsmith's 1839 map for the District of Adelaide is a point-centred circle which denotes the stations of the trigonometric survey. Tantalising stations in the legend. Click, although Light, and so this is what the stations that we are searching for. Although Light's and Ormsby's field books are not yet found, the field book of Assistant Surveyor Baltravis Finnis detailing bases and angles for the trigonometrical survey was preserved in the South Australian Lands Department. If you could click to the next screen, please. From this, in combination with two other fragments, we're able to piece together the methodology that Light used, as well as find over 60 of the trigonometrical stations. So if we click again, we can see that Light, as Surveyor General, divided the area into 3 sectors. Click again. He's supervised the survey north of the river, and the area south of the river was divided between 2 assistant surveyors, Ormsby and Finnis. And click again. Thank you. So if we go to the next slide, please. Okay, all 3 sectors were surveyed in the same manner and properly interconnected, and this enabled topographical data collected by all survey parties to be integrated and plotted to form the base plan for the design of the original layout of the rural sections and the road alignments, as Light had to plan the transport network for the entire area along with the subdivision for the country allotments. And click, next slide, thank you. So this is my contribution to the research. I found some charred pieces of paper in Light's collection, which I suggested to John seemed to be trigonometrical networks. This is one for the river at Port Adelaide, and the river sort of crosses through the diagonally from the bottom left-hand corner, right-hand corner to the top left, and you can see the ships are in the river, but the squiggle that you can see at the top is actually a tributary flowing into the Port River. And the next slide, please. This is a survey by Light in his own handwriting of an old course of the River Torrens. The squiggle running through the lower part of the image is the current course of the River Torrens and had water flowing in his time. The squiggle to the above that is a former old and defunct course of the River Torrens. And these are indeed trigonometrical records from the survey, and they provide us with further information about some of the original stations. Click. So this is the bulk of the information comes from a field book number 76, held by the Lands Department, preserved in the South Australian Lands Department, which was the bases and angles recorded by Baltravis Finnis in that southern and western quadrant, but he also made many connections to other trig stations in the other sectors. And this shows this is page 7, showing the measurement of the bases. And the next slide, please. So this is extracting some of that into a table. Again, I focused on the baselines as they were very significant trig stations for more than one reason. And next slide. Okay, so if we click a few times, we'll see the baselines appear. So firstly, the Flagstaff at the coast, and then trig station A, then station D and the first baseline, and then B and E, the next baseline. And showing some of the triangulation. If we keep clicking through this slide, we'll show other baselines and then other stations in the survey. Next slide, thank you. So this is what we've been able to ascertain by piecing together this information. So starting with the RSS map as a general indication of where we might expect trig stations to be, but then going to the specific data and trying to work out which trig station has which name. And so the first is showing the baselines, which we've already looked at, and on the right-hand side is the whole extent of the information that has been gathered from these multiple sources. Next, thank you. And now I'll relate the Trigg survey of the District of Adelaide to the Working Week theme by way of demonstrating that the Colonisation Commissioners for South Australia and their Surveyor General William Light provide us with an epitome of being a smart surveyor for land and water management in their 19th century new reality. So as you see there, Light used his experience of navigation and his experience, and he created an innovative solution to a complex problem. This is equally relevant today, or more so. Due to commercial and development pressures, society can be said to have gone backwards, willfully ignoring principles for sustainable development exemplified in the 1830s. So if we continue, next slide. So this shows, if we just go through, I've included these for completeness, but we don't need to dwell on them. This shows Light's, he's doubled the Cape of Good Hope 4 times. First as a child of 6 years old on his way to school from the island of Penang via Canton and the Sunda Strait, passing Krakatoa, which was visible from the deck of the ship, and then returning to India, to Calcutta for his sister's wedding. And then finally, the 4th voyage around the Cape to South Australia as captain of the survey brig Rapid and the first Surveyor General for South Australia. So next, thank you. And so this shows all the coastal explorations he had to do, tasked with finding the best site for a city. Next, please. And just a reminder to us that despite the transport by sailing vessels on foot with hand cuts and bullock wagons, they had state-of-the-art survey equipment with them. Next. Okay, so Light was very, very well versed in accommodating tens of thousands of troops with cavalry, infantry and artillery from his experience as a Deputy Assistant Quartermaster General in Wellington's Army in the Peninsular Wars. And he was particularly experienced with the risk of rivers rising rapidly. Next, thank you. He had to provide not only for drinkable water, but also for safe access for shipping. And next. And for land. So he's had to balance these competing interests, look for the best and prepare for the worst. Next slide, thank you. And so these are the advantages. If we can skip through several of these, is just for completeness. He was given a list of instructions. Next, thank you. And they were quite comprehensive. Yes, next. But he was delegated with the sole authority to determine the site and to lay out the plan of the city and the country sections. Next, thank you. And he tells us that it was a geographical position and his observations. So he applied all of his expertise and knowledge. And then additionally, he applied a great deal of observation and intelligent assessment of the southern coast, the Gulf and the coastline of South Australia.
Hello, I was muted. Sorry.
Next, thank you.
Hello.
Sorry, can I ask you a quick question, Claudia? I just finished the.
And he chose the most difficult location because it was on beautiful, gently rising ground and formed the best connection with the river. So the difficulty of the site did not deter him.
Can I speak now because I can hear somebody else? All right, okay. I seem to be able to hear somebody else. Kelly.
Yeah, she forgot to leave this room and now she's making a presentation at one of the speeches.
I'm sorry, click. So this shows the.
So I just was wanting to go to the AMA afterwards,
the next,
it was a separate link, but I clicked on what Janine gave me, and it didn't seem to work.
Look for the rising ground.
Okay. I'll just
next click.
Sorry,
the finer planes and avoided the swampy areas. So if we keep clicking.
Thank you.
Yeah, just 1 second.
Kelly, I think you need to close your Hopin help desk session. But now you are unmuted. So what you should do, because we cannot hear you anymore, you should close your Hopin help desk session or unmute it and mute yourself again. Thank you.
Sorry, what do I do?
Yes, we can hear you again. So please continue.
Okay, and if you could click again, please. Right, so, and again. So this assessment of the environment on the site, Light used in his decisions about where to site the City of Adelaide.
It's been sent.
So can we go to the next slide, please? Okay, Light and his team had no common work to achieve, performed it under no common circumstances, and had done it in no common manner, with limited means and limited time against all the opposition that he'd faced. South Australia was not a commercial venture. However, the Commissioner's instructions to Light left him in no doubt that the province's prosperity depended upon him to a very large extent. In this case, it was to lay the foundation of the state's sea and land transport network, land use allocation, public offices, public health and recreation reserves, and entailed a myriad of essential land and water management decisions. Light applied his expertise and knowledge of navigation to devise an innovative technique, the coordinated cadastre, with exemplary regard for the sustainability of his design and intelligent assessment of and provision for current and future needs. Future-proofing the city against flood and drought, provision for environmental and public health. Aware of the potential for future developments, he emphasised the essential knowledge and actions, trigonometrical survey, the importance of geography, diligent personal observation, research and consideration of current and future needs, is intergenerational planning. And to achieve the best outcome may require choosing the most difficult course with conscious purpose. Light and his survey team had succeeded in building the foundational spatial infrastructure that gave South Australia a chance to have a future. Thank you.
Microphone. Should not be muted. Can you hear me now?
I can hear you, yes.
Yes, okay, then I'm fine. Good. Thank you, Kelly, for your presentation. You're the last one in this series. Maybe there is an urgent question, then we can ask it to you. One question. I do not really see a question in the comment session. No, there are no questions so far. Maybe they come later on. Thank you very much, Kelly. We have also come to the end almost of this session, and I was just about to say that although, of course, in the preparation there are always problems and hiccups that we have to solve, that we in the end we did it I think very well. We managed to have very good presentations. We managed to have very nice video presentations, and I would like to thank the speakers for this, for the high quality, for their also their efforts to make a presentation and to contribute to this session. I think it was one of the best sessions I think I've attended during this e-working week. Please, but you are not ready yet. We still have a discussion session. So after this session, we will have the Ask Me Anything session. And I would in particularly recommend to join that session because we will start with a quiz. And the quiz is about, let's say, all the presentations. So if you have been carefully listening to the presentation, you must be able to complete the quiz. It's about 9 questions, so it's not that long. So please be invited to join us in the AMA session. Of course, you can always there ask all the questions that you still have for the speakers. And of course, you can have other chats and you can do some networking and greet the people that you haven't seen for so long time. If you cannot join the AMA session, please read the papers. In particular, those who have presented the video, they have much more to tell, and they have prepared very good papers, and you can find them in the proceedings of the conference. Then I would like to thank my partner, Tim Brouwer. Okay, we will see each other back in the AMA session, for his excellent work to introduce the speakers, but also to guide the speakers backstage in preparing their presentations. And next to that, I would like to thank Christelle van den Berg, who has been our technical support staff backstage, and she made this she is also the one who made this a wonderful session. I will see you back in a few minutes in the Ask Me Anything session. Thank you very much.